Okay, if you plot a graph of the number of pirates in the Caribbean against the average global temperature, you can see that as the number of pirates goes down, the temperature increases. So does this mean a lack of pirates is causing global warming? Well, no. This graph was produced to point out that correlation does not always imply causation, and that sometimes just because data produces a good graph doesn't mean you need to draw it. Now, graphs are powerful tools to visualize the patterns in data when used correctly, as our brain has evolved to be very good at spotting a visual pattern. You know, is that thing in the bush a tiger or just a bush? We are very good at spotting these patterns. However, all too often, graphs can be manipulated to prove or disprove somebody's point. Take this graph. Look at it closer. Notice anything? Well, firstly, if you look at the x-axis, besides the inconsistent scale, some of the numbers are the wrong way around, to deliberately deceive. Look at the data on this graph as well. Even if the years are not equally spaced, some are missing. So don't always take graphs at face value. In this video, I will talk about how we use graphs. To do this, I will discuss the different types of graphs and when we use them, how to draw a good graph and how to spot a bad one, how to draw your line of best fit, what the different patterns in graphs mean for that data, how to always get a straight line on your graph, and then what other quantities we can calculate or get from a graph. And then finally, we're going to talk about the errors and uncertainties in graphs. First things first, we need to discuss types of data. Generally, we split data into two types, discrete and continuous. Discrete data can only take certain values, for example, colours or car types, and it cannot be placed on a continuous scale. Continuous data, however, can take any value, for example, height. It can be placed on a continuous scale, like on a ruler. Now, take care. There are times when data looks continuous but is really discrete. For example, shoe size. This can only take a whole or a half number, can't take any value in between. So, in science, there are generally three types of graphs, depending on which data you are using. And whilst there are other types of graphs, they are generally just a version of one of these types. Right, our first graph type is the bar chart, the simplest of our graphs. We use this if we have discrete data as our independent variable, the one, remember, that we change. Now, there is a lot of debate with different people over whether the bars are touching or not. In reality, it does not matter. Just be consistent. Our next graph type is a pie chart. This is used if our dependent variable is a fraction, a proportion, or a percentage. These are useful for visualizing what fraction a result is of the whole. Our final graph type, the line graph or scatter graph. This is the workhorse of scientific graphing. These we plot if both sets of data are continuous, and they allow us to see how one variable is affecting the other. Normally, to do this, we draw a line, but more on these later. But what makes a good graph? The difference between a good graph and a poor one can make or break an investigation. Getting it wrong affects your ability to draw conclusions. To draw a good graph, remember the acronym SALT. S for scale. Make sure that the data on your graph fills more than half your graph paper. Remember, you don't always need to start at 0 on the scale if your data goes nowhere near it. You can use the breaking scale sign if you want to, or just start a few values below where your data starts. This way, you stretch the scales, making any pattern more visible. A is for axes. You should have a consistent interval or gap between the values. These should be a multiple of 2 or 5, as our graph paper normally has 10 squares per division. Normally our independent variable will go on our x-axis, and remember x is a cross, and our dependent variable will go on our y. Another way to remember this is independent is longer, so it's more likely to fall over. L for labels and lines. Label your axes with correct units, including any prefixes if you have used them. The correct line of best fit also needs to be drawn for your data, but more on how we do this later. Give your graph a title to tell your readers what it is. Normally, a title goes something like graph to show y, with y being whatever's on our y-axis, against x. Okay, so lines best fit. Now how you draw that line is based on some assumptions about your data. If we can assume that any changes in our dependent variable happen gradually over the intervals of our independent variable, because we have sufficient good quality data and we can clearly see this pattern, then we draw a smooth line of best fit through our valid points, ignoring any anomalies, things that don't fit the pattern. This could be a curve, or it could be a straight line. Now, judging if data is a curve or a straight line is a skill you need to develop. The best way to do this is to pick up a piece of paper and look along it. Then any pattern becomes apparent very quickly, along with any anomalies. If our data is of poor quality, or we cannot make assumptions about how the dependent variable changes in between intervals, so for example, something like a speed time graph, where we know speeds at certain times, but we can't say anything about the speed in between, then we connect our points with straight lines. The problem with using straight lines is we cannot use our graph to then interpolate intermediate values. So we try to avoid this at all costs. By that, what we mean is, if we've got to say a time at 30 seconds and a time at 60 seconds, we've drawn a straight line between those 2 points, making no assumptions. We can't have a guess at what the speed is at 45 seconds, for example. Okay, you've drawn the perfect graph. You've drawn your excellent line of best fit. You're then asked, what's your graph tell you about the variables? Well, there are 7 possible options. The first 3 relate to straight lines. Proportional, directly proportional, and decreasing at a constant rate. Now, proportional graphs have a straight line with a positive gradient that does not go through the origin. We can say that as x increases, where x is whatever is on our x-axis, y increases at a constant rate, where y again is whatever is on our y-axis. Mathematically, we could write this down as y equals mx plus c. where m is the gradient and c is our y-intercept. Now, gradient and intercept we'll come back to in a minute. Directly proportional graphs. These also have a straight line with a positive gradient, but this time it goes through the origin. Mathematically, we can say y is proportional to x. And that's what this alpha sign, this A, means, proportional to. Or y equals mx, where m is our gradient again. In these graphs, if you multiply a value on the x-axis by a factor like 2 or 3, then the value on the other axis is multiplied by the same value. So if you double one, you double the other. And this is a good way of checking if you've got directly proportional data. Our final straight line graph is decreasing at a constant rate. These have a straight line, but now we've got a negative gradient. The line slopes down. Here, as x increases, as x increases, y decreases at a constant rate. Okay, so what about other increasing graphs? We have increasing and increasing rates. Here, as x increases, y increases, but for the same increase in x, you can see that y increases by more and more as x gets bigger. We have increasing at a decreasing rate. So here, as our value at x increases, our y increases still, but for the same increase in x this time, y increases by less and less as x gets bigger. Okay, our final two graph types I'm calling them decreasing graphs. So, first one, decreasing at an increasing rate. Now, as x increases, y decreases. But for the same increase in x, y decreases by more and more as x gets bigger. And our final graph type is decreasing at a decreasing rate. As x increases, y decreases. But again, for our same increase in x, the amount y decreases by gets less and less the more x gets bigger. Now, bring to our graph types, but you'll probably agree with me, hopefully you agree with me, you might disagree on this. Curves are a pain. They can make the maths more difficult, they make drawing the lines more difficult, so if we can, we avoid them. To do this, we can manipulate the axes to get a straight line. So we take the equation y equals x squared. We plot the values for y for given values of x, we get a curve. However, if we plot instead y and x squared, so we keep y on our y-axis, but along here instead we now plot x squared, we get a straight line. And we can do this for any equation. Take y equals x to the power of minus 2. We write out the equation for a straight line underneath, y equals mx plus c. The terms should see some terms line up, so we plot y on the y and x to the minus 2 on the x, and again we get a straight line. So the equation for a straight line is y equals mx plus c. I mentioned before, m is gradient, but we said we were going to discuss this later. Now we're going to do that. So, gradient. What do we mean by gradient? Gradient is how steep the line is. It's sometimes referred to as rate as well, rate of change. It is calculated by dividing the change in y by the change in x, or we do y2 minus y1, where those are 2 points on our y-axis that are on our line, and x2 minus x1 is our change in x, dividing one by the other. Now C is our y-intercept, or the value of y when x equals 0. Normally, to get this, we extend our line of best fit back to where x equals 0 and read it off the graph. However, sometimes this is not practical. If the graph axes don't go back that far, we have to use the equation. So we take two values on your line of best fit, a value for x and a value for y for the same point. We rearrange our equation for our straight line to get c equals y minus x to calculate c that way. Alright, let's look at an example first then. Take the equation y equals a half gt squared. Now some of you may recognise this as an XUVAT equation. If we plot y against t, we'll get a curve. This is very similar to our y equals x squared graph we looked at already. However, if we compare again this to a straight line, if we plot y against t squared, we will get a straight line. It will go through the origin. And if we look at where m is on our equation compared to our y equals a half gt squared, you can see that the gradient here will be g divided by 2, or half g. Furthermore, we can use the gradient of a line to calculate a given quantity. So in our example, we could actually do these results, and we could get a value using the gradient for the acceleration due to gravity, g. Another example is if you plot voltage on the y and current on the x, the gradient will be resistance from Ohm's law, where V equals IR, or Y equals MX, R being the gradient. The final thing we can calculate from a graph is the area under the graph. This can be a different quantity again, depending on your equation. So if we have a force extension graph for a spring, if it follows Hooke's law, or F equals Kx, F is force, K is our gradient term you can see here, and X is extension. If we multiply F by X, force by a distance, we get energy. That's the equation for work done. So if we calculate the area under this graph, doing F times X to work out that area, we get the work done stretching our spring. Okay, again we're looking at A2 here mostly, but good for others as well. So, we can use a graph to display errors and calculate our uncertainty. However, this bit does depend on your exam board and your level of qualification. For WJC, we plot error bars on our graph equal to our uncertainty. So if we have a single measurement, this is the resolution. If we have repeat measurements, half the range. Now occasionally our error bars will be too small to plot, so don't plot them, don't try to. But remember, if you're on that, you have to state this on your graph. When we plot these error bars, we get a rectangle that our measurement could be in. This has an impact on our line of best fit. It could go through any part of the rectangle. So now instead of plotting a line of best fit, we attempt to draw two lines of worst fit, aiming for the steepest and the most gradual lines. This means the true gradient will be the mean of these two gradients, and half of the range will be the uncertainty in our gradient. In summary then, we select the type of graph based on the type of data we have. We use SALT to draw good graphs. We generally want straight lines, so we change our axes to get them. Our gradient is how steep a line is, or the rate of the line, and it is calculated by this formula. The intercept is where the line of best fit crosses an axis. Error bars are plotted as the uncertainty of a measurement, and we can plot then the steepest and most gradual line. We use the mean of this for our gradient, and we use half the range for the uncertainty. Again, thanks for watching. Probably want to do some follow-up videos of some demonstrations about drawing graphs, taking some exam questions. Coming up on the screen after me will be the playlist these are in, some recommendations, and obviously our subscribe button. It will be really good if people can subscribe to these. Again, leave comments if you want to see a certain type of video on something. I see that we've produced stuff now for a range of topics, and hopefully get some more done in the future.